One correction I just made on the assignment. When we talked about converging, so in part 2, whether the Q function is converging, it's useful also to use a sanity check and say, is it converging to what look like reasonable values? So I just added that here. And let me give you an example of what I mean. So if we look at, right, this is our terminal state here. Here, in this state, what's the optimal action? Just to go right. And what's the value of that action? So what's Q of 7, comma, going right? -1, that's the reward, right, for going to our terminal state here. So we have -1 plus whatever the value for our terminal state is, which is 0, right? We don't have any, there's no future discounted. So we have -1, and this is for the terminal state. There's more possibility though, right? What else can happen when we choose right? We could go down. So if we go down, so actually this 0.1 is going to happen 80% of the time, right? So our expectation is it's 0.1 times 8 plus -10 times 0.1, right? Because 10% of the time I go down. And then plus whatever the value is in this state here, right? So we've got some negative something here. So when we sum these up, the value looks like around, so this is -1, -0.8, so around -1 point, probably somewhere around -2. That's what I'm going to say. And we certainly would also expect that the value of going right from here is exactly the same as the value of going down from above the t, right? And then as we get farther away, like here, it's probably going to be about -4, probably, roughly, kind of, right? And so on when we get up to the edge. So look and make sure you're getting numbers that seem about like that. And if not, something's probably wrong. Right? Does that make sense? Okay. So today, so we are continuing on in reinforcement learning. Today we're going to talk about a couple modifications of the Monte Carlo method. And then we're going to talk about what's called temporal difference learning, or TD learning. And then Wednesday, we'll put this all together, combine our reinforcement learning knowledge, our neural network knowledge, and look at AlphaZero, the Go/chess/shogi, I don't know that game, but playing neural net. So this is a review. First visit Monte Carlo with exploring starts. Right? Why do we do exploring starts? Yeah, we're making sure we're visiting all state action pairs because otherwise we won't have any values for those Qs. So this ensures that we have a non-zero probability of starting in any given state and action. So we generate an episode, we find the return, right? So basically once the episode ends, we find our return for each distinct SA pair, and then we append it to our returns. And we say Q is the average of those returns. Right? Nothing new there. Questions? Well, here's what we can do. We can remove, so currently what we have is in our initialization, we set returns of SA to be an empty list for every SA pair. And then we, just like we said before, append G to there and set Q of SA equals the average of those. The problem with that is it's a lot of memory, right? In fact, in my implementation for a while, as I would increase more and more iterations and more episodes per iteration, it was taking quadratically longer, not surprisingly, because the returns was just getting bigger and bigger and bigger and bigger. So instead of doing this, let's just calculate our averages incrementally. Okay? So let's keep a count of how many times we have found a return for a particular SA pair. And then in our loop, each time we are looking at a particular SA pair in our episode, increase the number and then go ahead and update Q of S of A, right? And let's just see if this seems reasonable. So this is QSA minus QSA over NSA. So that's Q of SA minus 1 over NSA and G over NSA. So this should be basically just giving us a running average. Okay, so all we have to count, all we have to keep track of is the count rather than the actual list of items. Does that make sense? Or we should be getting the same answer. So the old Q is weighted n minus 1 over n, and the new reward is weighted, this is really, since we just increased n, yeah, is weighted 1 over n. Okay, so we can do that. And we just have a running average. Questions? Now what we can say is, well, let us make this modification. Rather than keeping a count, let's look at having some learning rate. So alpha is going to be our learning rate. So let's see what we're doing here. Here we're taking the old Q and adding to it the difference from our actual reward and our estimated reward. Right? So this is the target and this is our estimated. And we're then dividing that by a number that changes over time, but becomes our factor here becomes smaller and smaller. Right? Here we can say, let's just use a constant factor so that we are approaching sort of this G, if that makes sense. So this is going to end up, what would we call this? It's not a running average, right? This one's a running average. This is a exponential, yeah, exponentially weighted average, right? And so this would say that any rewards we've got, like in previous iterations, many, many episodes ago, don't really matter. So this will, as our policy changes and our rewards change, tend to count the more recent rewards higher. We're not going to actually use this, but I want you to just remember this form, that we take Q and we are updating it by a learning factor where we look at the target we're aiming for and what we have now. So this is kind of how far off we are. And this says, let's take us partway there. And so this is how the exploring starts, Monte Carlo would change if we use that. And when we're computing value functions, right? We have value functions both for the state and action pair and also just for a state. We can do the same sort of idea of having a learning rate update. Right? There are methods where we're actually directly updating the value for a state rather than updating the value for a state action pair, and in which case we just use this version instead. Okay? All right. So here's a pictorial example of our Monte Carlo, right? We start at a start state, and we are following our policy with whatever non-determinism is in the policy and in the environment, and ending up finally at some terminal state. And then we back propagate, interesting word, that reward all the way back up to each of the state action pairs. Okay? So let's look at this. This is the actual discounted reward. Which we might also call the target. So temporal difference says, rather than waiting until you have completed an episode and gotten to a terminal state, let's try and update after just one step. We're going to take one step, and then we're going to have a better idea of what our total discounted reward is than we had before. So we're in a state, we choose an action, we get a particular reward, we're in this state. So we know, right, the Bellman equation, Vs of t equals t plus 1 plus our discount factor times Vs of t plus 1. Right, that's how we define that. So if we know the value correctly for a particular policy, then this holds, right? So it's the first reward you get plus the discounted rewards from then on. We, in our Q functions, for example, we don't have an exact values for our policy, right? We have approximations. And to begin with, what are those approximations? In the assignment, what did we use? Q of SA got initialized to negative 9999, which is not right, right? But we successively get more correct ones. Here, we're using this one step, and what we're saying is this is our target. Okay? It's a better approximation than we currently have. And so we're going to move our value in that direction. Right? So this is sum alpha times target minus estimate. Right? And this becomes our new estimate. So in one sense, it seems like you've got a random value here that's not very good, and you've got a random value here that's not very good. How is this going to do us any better? Well, we do have one piece of real information. What's the real information we have that's not an estimate? The reward. We actually know this reward. This is real, right? So we are realer with this estimate than we are with the estimate up here to begin with, because we actually have a reward. And when we get to the very bottom here, and we end up in a terminal state, we're going to be able to move back to the previous state and have no necessity to do v of st plus 1, right? We know the value of this terminal state for sure. And so we can move this back 1. It won't help this yet, right? Next time we run, assuming we happen to pick the same path, this one's correct, and now this one will be correct. And as we move back up, this one will be correct and so on. And this won't actually be correct because it depends what path we take, right? We'll have one path in the subtree starting here that'll be correct. But we will successively approximate our correct value. Okay? So TD just says take one step and use that as your approximation. The real reward you got plus your estimate of the new state. True.
In the actual computation, how does it know the recursive value of v of st plus 1? Doesn't that need to be kind of calculated explicitly to
So here's what we would do. Initialize v of st's to random values.
Okay.
And then we're going to go through and update this. Just like in the assignment, once you do it, the q's get initialized to, you could do random, we did -9999, you could do 0, whatever. Just some initial values that are arbitrary. And then we will get better and better. You could think of it kind of like Newton's method, right? You know, to try and find a square root. We take some arbitrary guess and we work our way from there. So we're iterating. Questions on this?
No one actually does the recursion because it's too large, so they just initialize it to random values.
No one does the recursion, no. So, I mean, it's too large. You could theoretically solve these, simultaneous equations, but no one does. The one thing you can do is you can do, just kind of cruise up here. So you could do dynamic programming. It's not quite the dynamic programming you're accustomed to, where it's sort of one pass down, if you look at it recursively, or you're filling in a table if you're looking at it from the bottom up. Instead, the idea is start at a state, like here, and you have to know the model for this to work. So assuming you know the model of exactly what these probabilities are, what's the probability? So this is the policy. What's the probability of A given S? And these values, what's the probability of S given the old S prime given the old S and A? If you know all these, then what you do is calculate or use the current values of V's for all of your children, and then use the probabilities that you know and compute now your weighted value. It's not correct because your children's weren't correct, right? But you then do this and iterate over all states and continue doing this multiple times and it will converge. So we don't have any sort of sampling or randomness here. And you're not actually executing the policy. You are just figuring out, if I have the policy, I can figure out for a given state what the probability of each action is. The environment tells me, assuming I know the environment and the model, given each state action pair, what's the probability of a new state and reward. Right? So I can figure it all out. And I left out one thing in describing this. So yes, you have to know the estimates of the values here. You also need to know the rewards that are coming out, because you're going to actually use that as some ground truth, right? In one step, what's the reward? What are the values? But in the TD approach, we're taking a single path down. In the dynamic programming approach, we're looking at the entire, all the children in the tree. So here we're doing this bootstrapping where we start with an estimate, right? We have an estimate and we're continually improving the estimate. The Monte Carlo, we're just rolling the dice, taking our results, averaging them. We don't have any pre-existing estimate that gets used in any way. Okay. You notice, for example, again, back to the assignment, where you initialize Q of S8 at negative 9999, but then as you're calculating the new Q, you just throw that away and find the average of the results. All right. So the weight decay Monte Carlo, this was our target. The actual real return that we get after time t. The problem is you can't know that until you've gone through the entire episode. So we don't want to wait. We instead are going to use our estimate of what the return will be. Our real value of what the reward was at this time step, plus then our discounted estimate of what it'll be at the next time step. Okay. So let's look at an example of how Monte Carlo would be different, let's say, from temporal difference. So this is an example. You're leaving the office Friday at 6. 0 minutes have passed, and you want to predict how long it's going to take to get home. So it's going to take 30 minutes. So the predicted total time at this point is 30 minutes. Okay? And then you get to the car and find that it's raining. All right? It took you 5 minutes to walk to the car. Since it's raining, you predict you have another 35 minutes. So your total time you're predicting now is 40 minutes, which made sense because you got to a new state, you found it was raining, you updated your prediction. And then, as you're exiting the highway, it's been 20 minutes, and your estimate is you only have 15 more minutes. So now the estimate is it'll only take 35 minutes. So just a question, what happened here? How did we go from 40 to 35? It could have been good traffic. Maybe it's not raining as much. I'm not sure. Right. But somehow our estimate for the particular time to go here was not accurate. Right? It was too big. All right, so let's see. We're 30 minutes in. We're behind a truck. We expect 10 more minutes. So the predicted total time is 40. And then actually, by the time 40 minutes come, we're not home yet. We're close to home, but we're not home. And we predict it'll be 3 minutes to get there, and it is. And we're done in 3 minutes. All right, so let's see what would happen if sort of this is the episode for Monte Carlo. And let's say, in some sense, this is the total reward, right? Our prediction is our reward. So our final reward is 43, or our final target is 43. Each of these should be updated to we're going to assume we have no discount factor, or a discount factor of 1. By the way, I was trying to write up an assignment. It turns out if you put in a discount factor of 0, like it's no wonder things aren't working. I had this problem, right? There are lots of ways you can get code wrong, and I seem to get every one of them wrong. So if we have a discount factor of 1, then the reward just propagates all the way back, unchanged. And so that would say, well, if you want to update your prediction, you should really update it to say, it's 43 minutes. at every time step from the beginning to the end. Now, does that mean every time you're going to leave the office, you're going to predict 43? No. You're going to make a prediction for today and tomorrow and the next day and the next day, and then you'll just take the average of those. Right? So you might say today was an unlucky day. Maybe actually you never make it home in 43 minutes. Maybe that's the fastest you could ever do it. Who knows? But here's how the TD would work. The TD would say, when I'm leaving the office, my estimate was 30. Okay? When I reached the car, I had some new information, right? I know how long it's taken so far, and I know what my new estimate is. So at this point, the prediction is the total time is 40. So I should go back and update this. Okay? If I have a learning rate of 1, I'll update this to 40. If I have a learning rate of 0.5, I'll update this to 35. But it's going to pull this up to try and match with the next time step. And similarly, this estimate is going to get pulled down because when we got to the next state, it was less than what we thought here. This one will get pulled up, this one will get pulled up. And so that's how we see this here, where the first one's going up, the second one down, and the latter one's up. Does that analogy make sense? That's how that's working. You have to kind of stretch it to come up with rewards and things like that, but that's the basic idea. We can just take a single step and make an update, take a single step and make an update. So there are several advantages of this over the Monte Carlo. What might one be? Say that again? Faster in what way? Faster convergence because? Yeah, we can update every single time step. We can update our value function. Right? We don't have to wait until an entire episode before we update our value function. What else? What if we have a continuous game or a continuous environment? Right? I'll give you an example. Let's look at life for one of us. It's not continuous. It does end, but a long time from now. And we don't really want to wait until the game is over before we start evaluating our value function and our actions that we're going to take. Right? We want to go ahead and use some intervening rewards to decide what to do. So if we have an infinite game, right, if we have something that might never terminate, then Monte Carlo is a bit of a problem, right? Because we've got to wait for the episode to get to a terminal state, and if either there is no terminal state, or much more likely, we might have a policy that takes us back. Like let's say we get into a state and our policy says, go back to that state. That's not quite true. Our policy says, take this action. The environment says, take us back to this state. Right? So our policy, if we're in this room, is, our action is sit. And the environment says, well, if you're in this room and you sit, guess where you are? In this room. Okay? The terminal condition is like down in the cafe. But we'll never make it there because we got stuck here. Will exploring starts help us? This episode will never end. We might have had all the episodes starting in all different places, but this episode, we're stuck here. It'll never end. Okay, did I have this as part of my trying to do the assignment? Yes, I did. So what do we need to do to avoid that? What can we do to a policy to make sure that it will eventually try everything? So this is like our Band-Aid to make sure we don't get stuck. And what you can do is do an epsilon greedy policy. So basically, take pi, sort of apply an epsilon greedy to it to come up with some pi prime. Where epsilon greedy says, you know, with probability epsilon, we're going to choose a random action. Uniformly. And with probability 1 minus epsilon, we're going to do pi prime of A. Sorry, of S. So this guarantees with some non-zero probability that we'll walk out the door, right? If that's one of the actions you can take from this state. And that has a non-zero probability of walking to the stairs, and there's a non-zero probability of going down the stairs and then turning left and then going in the cafe and then finally terminating.
So can you go to that formula again, please? The pi of S. So
Yeah. So let me rewrite it so it's not all ugly. So pi of S, sorry. Pi prime of S is, with probability epsilon, we're going to choose a random action uniformly. And the 1 minus epsilon, we're going to take pi of S, right? So epsilon greedy, yeah.
Wouldn't your optimal policy just be to go somewhere else this time?
So we're going to get to this too, right? So an optimal policy is probably not an epsilon greedy policy.
Right, I'm saying, like, why would you, like, say, like, the example you gave, like, in this room, wouldn't, like, the correct policy just be get out of this room instead of stay in this room?
Sure. But remember our situation when we were doing Monte Carlo. And in general, this general policy improvement is you have a policy, you evaluate it, and then you improve it. You evaluate it and improve it. We're evaluating it using Monte Carlo. Our evaluation is take the policy, whatever policy it is, and run and see what happens. If that policy is a stupid policy, it could end up in a loop, right? Does that make sense? So yeah, smart policies don't end up dead-ended getting no reward or getting negative reward or whatever else. But we don't require smart policies. We try to build smart policies from stupid policies. Does that make sense? I thought your question was going to be an epsilon greedy policy. Let's say pi is an optimal policy. Is pi prime optimal? No, pi prime some of the time is doing the wrong thing. But when you are creating the optimal policy, it's nice to be trying everything and exploring. And the epsilon greedy gives you exploring. So maybe what you do is you have an epsilon greedy with a epsilon that trails off over time. So you reduce the epsilon value from 0.1 down to 0 over so much time. And then you will end up with an optimal policy. Make sense?
So you're decreasing your epsilon over time?
Decreasing your epsilon over time. So larger epsilon means more exploration, right? Because we're doing random stuff. Smaller epsilon means more what? Yeah, exploitation. Exploitation, yeah. So someone spent some time coming up with these words and they're pretty good. They, you know. Is it alliteration? Yeah. So. Okay. TD methods don't require a model of the environment, only experience. The Monte Carlo methods require a model of the environment. Do I have to know what all the probabilities are of all my transitions from one state action to a reward new state? Do I have to explicitly know that? I just have to have some way of either simulating or running in the environment and see what happens. Right? I don't have to know what the probability is that it's going to rain tomorrow. I can just wait till tomorrow and I'll have one sample and that tells me whether there's raining or not. It's probably not a great example because it's hard to, across the multiverse, right? We could look and see whether it's raining tomorrow in all these universes. Another example might be, what's the probability when you're speeding that you're going to get a ticket? I don't know. I can estimate that by speeding lots and lots of times and counting how many times I get a ticket. So TD and Monte Carlo both don't require a model of the environment. But dynamic programming does. Okay? Because dynamic programming says I'm not going to take a policy and try and figure out its value and then iterate that. I'm going to just compute, given that I know everything about the world, okay, and everything about the policy, and just compute what those values are. I still have to iterate. TD can be fully incremental. We don't have to wait. We can learn before we know the final outcome. We can learn along the way, right? Which is a good thing as our value function gets closer and closer to reality. Less memory, which is good. We don't have to have the final outcome ever. There might not be a final outcome. We might have a sequence that doesn't quite complete. And they both converge. But there's something interesting about that convergence. Okay? And that is, they both converge to different values. So assume we're doing some batch updating. So we have some data. We train on k number of episodes until we converge. And we'll just do a complete pass-through. TD will converge. Monte Carlo will converge, but you get a different answer. Let me explain why you get a different answer. So let's say, here's our episodes, right? This kind of reminds us of last week where I just said you're in state A or state B, what action do you want to take, right? So we're in state A, we get a reward of 0. We go to state B, we get a reward of 0, and we're done. Now we go into state B, so we start in state B, we get a reward of 1. And again, and again, and again, and again, and again, and this time we start in state B when you get a reward of 0. So these are our 8 episodes. What is the value of state B? I mean, as best we can tell, it's 3/4, right? And that's what Monte Carlo would tell us. Right? Monte Carlo would tell us, this time we get a 1, so we propagate that to this state. Here we get a 0, propagate it to that state. Here we get a 0, propagate that to B. 0 plus 0 will propagate back to A. Okay? So B is going to be 0.75, but what's A going to be? How many episodes did we have that had a state A in it? 1. What was its reward? 0. So what's the value? 0. Okay? But the problem is, if we think of our state diagram, kind of here's what we know. A goes to B 100% of the time, and B gets a 0 reward 25% of the time, and 1 reward 75% of the time. And this is what TD will figure. TD is going to figure if V of B is 3/4, and 100% of the time A gets a reward of 0 and then goes to B, that the value of A should also be 3/4. Say that again. So let's look a second and see what each one of them is converging to or minimizing or maximizing. Okay? But yeah, it seems righter, right? So the prediction that best matches the training data is VA equals 0. Okay? The mean squared error, right? It fits the samples we've seen better. A gets 0 result. B gets 3/4. Fits perfectly. All right? It just doesn't generalize very well. And that TD generalizes, where basically we're looking at we're producing the most likely Markov model for the results we've seen. Yeah.
Sorry, I know it's a statistics term, but how do you define a maximum likelihood estimate? Like, I don't understand the term.
We can just say, all we have to think of is just if you think of all models with the two states, A and B, and what the rewards are, just look at all of them and what's the one that would have been most likely to give us the results we just saw. Okay, that fits our data. So the Monte Carlo kind of ignores the fact that we're assuming we have a Markov model here. And the TD does not. Questions on that?
So which one gives the maximum?
The maximum likelihood is TD. So this is TD, and this is Monte Carlo. All right, so far, one step. We looked one step ahead. Model-free, I'm ignoring the word tabular for a moment. Model-free means we don't need to know the model. No one needs to tell us what all the state transitions are in the environment, right, and rewards. And temporal difference, does that make sense, right? Temporal difference because we're looking at the difference between our estimate at time t and our estimate at time t plus 1, where we have had a real reward along the way. They work well. They work well in incremental fashion. If the world is Markov, then they'll learn better. The Monte Carlo methods fit the data better, so they have lower error, but they will have higher error in the future. They're less likely to generalize. So here's TD learning. TD learning, we have one step. We have state, action, new state. Okay? And we're going to back up from there. We're going to back up our estimated value here and our real reward to come up with a new estimate. The Monte Carlo, we go through an entire what's it called? Episode, thank you. So we go to an entire episode and then we back it all the way up. So this is deeper in terms of how far we're backing up. Monte Carlo versus temporal difference. And there are things in the middle too that we could use. So we don't have to be at one extreme or the other. The width of the backup says how many children are we looking at basically from the current state. In TD learning, we do use one action, which is the action we get from our policy. In dynamic programming, we look at all actions that the policy could generate. And then look at, we don't have to simulate the environment and see what reward we get. We just go and look up what the reward is. Okay? And then this does one step. You can imagine an exhaustive search that just starts here and goes all the way down until it gets to terminals everywhere. and then goes back up and figures the probabilities of every one of these paths, because it knows the probability for each transition, some from the policy, some from the environment, and multiplies those by all the rewards we're getting all the way, right? There's interesting here. So if we're going to estimate that, flip back a second. All right, so if we're estimating that G sub t is equal to R t plus 1 plus gamma. This is not an estimate, this is truth, right? So we're saying that the value of S of t, because the value of S of t plus alpha times the target minus the S of t. And we said the target is equal to the reward we get now, RT plus 1, plus our discount factor times the ST plus 1. Okay? Well, this is looking one time step. What if we look 2 time steps ahead? Wouldn't that be even a better estimate? So that'd be R t plus 1 plus gamma times, well, V of ST plus 1, we can estimate that, right, as R t plus 2 plus gamma Does it seem like it'd be more precise? If we continue this indefinitely, what do we end up with? It's not exactly an exhaustive search, it's the Monte Carlo. We're going to say we're ending up with our final discounted, we're just calculating the discounted reward until we get to a terminal state. So we could do this 1 step, 2 steps, k steps. And it's exactly intermediate between temporal difference learning and Monte Carlo. TD lambda, I believe, does an average. So you actually average the, okay, so TDK is k times steps ahead, and TD lambda is the average of TD for many k's. Okay, stopping at some point, so you don't end up as a full Monte Carlo. All right. We've been using state value functions, and we're going to head back to state action value functions, so the Q's. So we have a state. We have our policy pi. Our policy pi tells us what action. We get back a return. We go to a new state. We continue on and continue on and continue on. And so what we're saying then is we just update in this case, we're not updating the value function, we're updating the Q function. So Q is equal to Q plus our learning rate times the reward we got, plus what? If we're trying to use the Q function, then we need a state and action pair, right? So we have a state, ST. We went ahead and we took an action, AT. That gave us a reward, T plus 1, and put us into a new state, T plus 1. Right? If we're using Q functions, though, we don't have Q of ST plus 1, because Q requires a state and an action. It says, what's the value of, in this state, you first take the action, and then you follow the policy. Right? Well, so what we could do is just ask the policy, what action do you want me to take? And then find Q of this. So we need the old state, an action, the reward, the new state, an action. That makes sense or not make sense? And it's important if it's terminal, our Q's are 0. So here's what we're going to do. Right? We're going to initialize Q to be something arbitrary. Except if it's a terminal state, we'll set it to be 0. By the way, as I was doing your next assignment, didn't set the terminal state to be 0. It's like, why are all my values just all wrong? Because I was propagating non-zero back. Anyway, I know all the ways to get stuff wrong. And then what you do is take an action. Okay? We observe R and S prime. And then we know we're in S prime. We need to choose A prime, right? The next action to take using our policy. And then we update Q. And then now go to our new state and our new action and keep going. So a couple of things. One, using a policy derived from Q. So we could just say our policy is, so here's one possibility, a greedy policy that says look at the Q function and determine for a given state, right? Because remember, pi takes what? The pi function takes what as a parameter? Takes a state, and if it's deterministic, and let's just say it's deterministic for now, it returns an action. So we could just define pi of s to be return max a over all q of s comma a, right? I'm just abusing syntax here, right? But basically we just want to find the highest, the a that gives us the highest value here. Right? So I don't really even have to have a separate policy. I can just always look at the current Q function. And that means every single step we take, the Q function is getting better and better. And so our policy is getting better and better. Now, there might be a good reason that we don't want to use this greedy policy. Right? Because the greedy policy might get stuck in this room. So we might want to throw an epsilon greedy on top of it. Right? Does that make sense? Yes?
The lowercase q and the uppercase q, is there a separate difference?
No. Same Q.
And in this algorithm, we are just looking one step ahead now.
We're just looking one step ahead, yes.
A prime.
Yep. This is called SARSA. Okay, it's called SARSA because if we look at the values, so basically we have a state, we have an action, we have a reward, we have a new state, and we have a new action. So old state and action saw, rewards are new state and action saw again, SARSA. This has the word here, on policy. So before I get to the on policy, let's use some sample data that I obtained last week from some unwitting folks. So let's use the TD approach here. So S is A, the action is 1. We have, let's say, our learning rate is 0.1, right? This is our discount factor. All right. And S prime equals A, and A prime equals 1. And what's R equal? Plus 10. Okay, so we're starting out as 0 for all these. What's our new Q of SA going to be? I'm going to just say plus equals, so I don't have to write that. So plus equals 0.1 times, what's our estimate? So what's at the right hand of this? Our estimate is the old value of QSA, which is 0. And what's our target? 10 plus 0, right? Because that's this Q of S prime A prime, which so happens to be SA. It's the same thing. So Q of SA is now going to become 1. Okay, and we don't do discount factors. We hardly ever do discount factors in examples on the board, right? Because they're too difficult. So now we have an update that S of A1 equals 1. And I have a small cheat sheet to make sure I don't get these wrong. Okay, so what do we do next in our calculations? S is equal what? A, and A is equal one, right? We did the first one. We're done with that. Now we got the next one. Reward is still plus 10. S prime equals A prime equals 2. Okay? So Q of A1 plus equals 0.1 times, what's our target? $10, which is our reward, right? Plus our discount factor times Q of A2 minus Q of A1. So Q of A1 equals the old value of 1 plus, this is 10 plus 0 minus 1, right? So it goes from 1 to 1.9. If any of this is not making sense, please let me know. It seems like this would be a good thing to be a easy thing to have on a test. So. Go ahead, Jillian. Because we initialize them all to 0 to begin with. So, good question. Okay, and now we are going to look at Q of A2, right? Because we're done with Q of A1. So plus equals 0.1 times the reward, which is -10, plus alpha S of B2 minus the old so this is 0.1 times -10, right? -1, yes. All right, Q of B2. In fact, I'm going to just give you a couple of them, and we'll go on. In fact, let's just move our way around. Let's say Q of B2 is 2.2, and Q of B1 is 2.2, and 1.8 and -1. And let's just run this one, okay? And what's interesting to realize is theoretically what would have happened is our policy here could have been based on our Q function that we had so far, on this Q function, right? It could be using that, although I don't think it actually was. So Q of A2 plus equals 0.1. The reward is -10 plus Q of B1 minus Q of A2. -10 plus 2.2 plus 1. -10 plus 3.2, so that's 6.8. So we're going to call that 0.7, okay? So that I don't have to keep track of one number. So Q of A2 equals -1.7, right? Huh. 2.2, 3.2. Yeah. So my slide, my notes got it wrong. Q of B1 plus equals 0.1 times the reward we get is 20 plus the discounted Q of A1 minus Q of B1. $20 plus 20 minus 0.4, so 19.6. So we'll call that times 0.1 is 2. No, 1.9, 19.6, 2.0. Okay, plus 2. And if we continue on, I think this $1.9 should probably be what we calculated before. And I'm not going to go through and calculate these, but you get the idea? Yes?
So in the Monte Carlo method, like the state action pairs that you are updating were always the first ones that appeared top down. Over here, do we do it explicitly for each step?
Everyone. We don't keep track of whether it's the first. It's in every. update for the TD. Yep. Yeah, so we might update Q of A2 10 times in an episode. Okay. All right. I mentioned SARSA was on policy. So on policy means the policy that you're optimizing, that you're trying to get better, is the same policy that's generating your episodes, right? A trace is also known as an episode. And in an off-policy environment, the thing you're optimizing is not necessarily the thing that's generating your behavior. So you've got one policy that's telling you what to do in your environment, and another policy you're trying to optimize based on this first one that is generating behavior. The policy that's generating behavior should be exploring, and the optimized policy should be, yeah, not exploring, but we have a name for that. Exploiting. Yeah. Okay. So how do we get policies to do this? So let's look at the windy grid world. So windy grid world, this is our starting state, and this is our terminal state, our goal. So we're trying to get to here. We can move up, down, left, right, but some of the columns have wind that goes up. So here, for instance, if you move right from S, you go to here, and you move right from S, you go to here. But if you move right again, you move right, but you also get blown up one. Okay? If you move right again, you get blown up one. If you move right again, you get blown up two. There's no penalty for going off the edge. You just don't go that way. So if we're at our S state and we go left, we stay there. Sorry, there's the standard penalty of -1 for every move. Okay? And our goal is, as always, maximize our reward. We terminate when we get to the goal. So here's what SARSA would give us. So this is an optimal trajectory. This is not a policy because there's no up and to the right. That's not a valid action, right? This is just showing the fact we tried to move right and it also moved us up one. And we tried to move right and it also moved up one. And we tried to move right and it also moved us up two. And then we went over and down and came this is not the optimal policy because this doesn't get us to G, does it? If we're here, how can we get to here?
They move you up when you move from there. Yeah, it's like when you're starting at start, you start moving to the right, you don't get moved up.
Oh, you're right. Interesting. So my implementation of it didn't. So, and that's right. Mine actually went down here and then up and then up. So for my optimal policy when I was implementing this. So, Laura. Here? Well, we're already as far up as we can get, so it doesn't hurt us there.
It's not like we move indefinitely up. It's if you
No.
try to leave the boundaries, you just stay.
Yeah, there's a wall there. Another question. So we're here. We move. Oh, it pushes you when you leave, right? Is that what we're saying? I'm sorry, I'm a little slow there. So we move in here. The wind doesn't hit us yet because it hits us when we leave. And so then we move to the left and get pushed up by one. So you can see after you're using SARSA that we are getting to what looks like our, well, so what should the cost be? Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Why do we have this squiggliness? And why does it look like it's somewhere more like between 15 and 25? Is our policy deterministic? Not according to this, and the reason is because we're doing epsilon greedy, right? Because if we didn't do epsilon greedy, then we get stuck and we would never make it to our goal probably. So we're doing epsilon greedy for our exploration. We're also doing epsilon greedy for our final result, which is unfortunately not going to be optimal. So the solution is what's called Q learning. It's basically off policy. And here's why it's off policy. So what we used to have here was Q of ST plus 1, A T plus 1. And where did A come from? AT plus 1 came from, who decides the actions? Nope. The environment decides rewards and states. The policy, right? So this came from our policy. And now we're saying no. When we're calculating the reward, don't look at the reward you'd get from the policy. Look at the best reward you could get, right? Look at the immediate reward you just got, plus the reward that you can get from that state, not if you follow the policy, but instead if you chose the best thing. So this has got to be at least as good as following the policy, right? It's no worse than following the policy. And that's really the only change here. So Q learning is all off policy. What we are optimizing is our Qs such that a greedy algorithm will be optimal. So let's look at an example. So here's another grid world. So this is the cliff world. We start here and we're ending in here. If we enter any of these states, it sends us off the cliff and we're like Hubert, I don't know if you remember that. You get minus 100 and it teleports you back to the start state again. You get to try again. So Q learning learns this path. Okay? Q learning creates a daring policy, right? Because the daring policy says, I will walk next to the cliff and I will just keep going right. And I will get to G. Is that the best you can do? So the environment, there's no randomness in the environment. There's no wind that's going to push you off the cliff. So that's the best you can do. SARSA comes up with a different policy. It goes all the way up as far as it can get from the cliff, walks along, and then comes back down. Why? Carl? SARSA is using the epsilon. SARSA is optimizing the epsilon greedy. And so SARSA is saying, well, this stupid epsilon greedy policy, if we're too close to the cliff, occasionally it's going to take us off, and it costs us a lot. So therefore, we're going to stay as far away from the cliff as we can, because that'll give us the most reward. And we can see in SARSA This is kind of the reward you get. You end up averaging about negative 25, but although sometimes you can get some big steps. And this is even smoothed. And this is the Q-learning applied to that same epsilon greedy policy. If we apply Q-learning to the greedy policy, we know exactly what it'll do. It'll be completely deterministic, and we know its cost. But if you apply it to the epsilon greedy policy, actually a bad thing will happen. We're going to be daring, and we're going to get negative rewards. And what you can see is the average is more like around 40, whereas here it's more like around 25. So the Q-learning is doing worse. The optimal policy it generated is better, but how it operates on our exploring policy is worse. Okay? So this is not actually bad. This just means don't use the epsilon greedy policy, use the greedy policy, because that's what Q-learning was trying to create for you. All right. We're going to skip expected sarsa, so we may just never learn that. The last word I just want to say is tabular. We created a tabular because we had a list of all our QSAs, right? QA1 equals this. QA2 equals this. We had a Q value for every possible state and action pair. That's great if we have a small number of state and action pairs. But if we have a huge number of state and action pairs, actually having a table for all of them is impractical. So we're going to have to approximate a function. What tools do we have to approximate functions? Neural nets. That's what we're going to do on Wednesday. So we'll see you on Wednesday.